Okay, so we are going to move on to the next lesson, which deals with solving quadratic inequalities. And this is something that we'll see again later on in the school year, working with polynomial inequalities and rational inequalities. And this concept, super important when you get into calculus. You're going to be doing a lot of solving inequalities in that class. So we're going to take like what we've learned with quadratic functions and then utilize it to help us solve inequalities. So directions ask us to solve the inequality in the real number system, and then we're asked to write the solution in interval notation. And for number one, we're given the function x squared minus 4x minus 21, and we want to find where that is less than or equal to 0. Okay, so the way that I'm going to suggest you guys work these problems out is number one, you want to make sure all of your terms in your quadratic function are moved to one side of the equal sign so that you're comparing your quadratic function to 0. And then the second thing I'm going to recommend is I like factoring, especially if I'm factoring, which you're going to be doing for a lot of these problems, I like factoring where my squared term is positive. So if your squared term is not positive, you can multiply both sides of your inequality by -1 to make it positive. Or you can think about like moving all of your terms in the inequality to the other side of the inequality symbol. Okay, so again, I'm going to do all these examples where the squared term is going to be positive. Okay, so we have both of those things present with this example. So what we want to do is we want to find the zeros of our quadratic function. And the first technique I'm going to recommend when you guys find zeros is to attempt to factor, because that's the fastest way for you to find the zeros. The problem is not all quadratic functions are factorable, but there's a quick way for you to see if it is factorable. And if it is, it's going to satisfy the x method for us. So we're looking for two numbers that multiply to give the top number. So that top number is going to be -21, the constant, times the leading coefficient, which is 1. So -21 times 1 is -21. And then add to give the bottom number, which is -4. That's the coefficient of the middle term. And there are two numbers for which that occurs. That is -7 and 3. Okay, so that tells me I'm going to be able to factor my polynomial. Okay, so I'm going to factor that quadratic function by taking that middle term and splitting it into two terms. So I can break up -4x to be -7x plus 3x. And then I'm going to factor this resulting polynomial here by grouping. So I can factor an x out of the first two terms, which leaves us with x minus 7. And then I can factor a +3 out of the next two terms, which leaves us with x minus 7. So x minus 7 is the common factor. So I'm going to factor that out. And when I factor that out, that leaves me with x plus 3. Okay, so what we want to do is we want to figure out the two values of x that make each of those factors 0. Okay, and the two factors of x are going to be x is equal to 7 and x is equal to -3. Okay, so what I want to do now is I want to put those two values in order from smallest to largest on a number line. Okay, so I'm going to put -3 as the first value and 7 as the next value. And I'm going to show you two ways that you can test. Okay, the first way, this is going to be the way that I recommend that you guys test, is to pick a number on each of the intervals. So we have 3 intervals. The first one is from -infinity to -3. The second one is from -3 to 7. And then the third one is from 7 to infinity. We're going to pick a value on each of those intervals to test to see whether that product is going to be positive or negative. Okay, so if I pick a number smaller than -3, let's say I pick -4, when I plug -4 in the place of x, that first factor, -4 minus 7, is going to be negative. The second factor, -4 plus 3, is going to be negative, and a negative times a negative gives us a positive product. Okay, I'm going to pick a value on the middle interval to test. So I think the easiest value for me to test on the middle interval is 0. So when I plug 0 in the place of x, we get that first factor to be negative, the second factor to be positive, and a negative times a positive gives us a negative product. And then if I pick a value bigger than 7, let's say I pick 8, when I test that, 8 minus 7 is positive, 8 plus 3 is positive, and a positive times a positive gives us a positive product. Okay, so what we are trying to find, we're trying to find where that product is less than or equal to 0. And when we look at our interval, the only interval for which we are less than or equal to 0 is the interval from -3 to 7. And then because the symbol is less than or equal to, we're going to use brackets at those values. Okay, if our inequality symbol was less than instead, our interval would be open and we would use parentheses at those values. Okay, so that's my recommended method because I think that's going to work best for you, not only in this section, but in later sections. Whenever you're going to be working with polynomials of degree higher than 2. Okay, but there's another way that you can determine this as well, and that's by thinking about what the graph of your function looks like. So because the function x squared minus 4x minus 21, because the coefficient, the leading coefficient, the a value, okay, that's a coefficient out in front of x squared, because that coefficient is positive, that means the graph is going to open up. And then 7 and -3 are the two x-intercepts for that graph. So if that graph is going to open up and have two x-intercepts, that means that the graph is going to have a vertex that lies below the x-axis, and that parabola is going to open up like so. And then you can look at that small graph that you've drawn and determine that on the leftmost interval, the function is going to be positive. On the middle interval, the function is going to be negative because the graph lies below the x-axis. And on the rightmost interval, the function is going to be positive. And that works fine for quadratic functions. When you get to polynomial functions of higher degree, like I said, that's not my preferred method, but that would work fine for you here. So if you want to test values, that's fine. If you want to look graphically, that's okay as well. Both of those are effective for determining the intervals which the product is positive or negative. Okay, so let's take a look at number 2. A little bit more complicated here in that we've got terms for our quadratic function on both sides of the inequality. So I'm going to move everything over to the left-hand side here, and then I'm going to write the terms like the quadratic function in standard form. So I want the highest degree term first, then the lowest degree term last. Okay, so I can write that as 6x squared minus 5x minus 6 is less than or equal to 0. Okay, so we're going to check and see if this is factorable first. Okay, so I'm going to multiply the leading coefficient times the constant. So 6 times -6 is -36. That number goes on top. The coefficient of the x term, -5, goes on bottom. So I'm looking for two numbers that multiply to give the top number and add to give the bottom number. And those are -9 and 4 respectively. Okay, which tells me that that quadratic function there is factorable. Okay, so I can take that middle term and break it up into two terms. The first one being -9x, and the second one being 4x. And then I'm going to factor this polynomial here by grouping. So when I look at 6x squared and 9x, The greatest common factor of both of those terms is 3x. And when I factor that out, that leaves me with 2x minus 3. When I look at the next two terms, 4x and negative 6, the greatest common factor is positive 2. When I factor that out, that leaves me with 2x minus 3. So 2x minus 3 is the common factor. When I factor that out, that leaves me with 3x plus 2. Okay, so we want to figure out where each of these factors here are going to be equal to 0. So 2x minus 3 is equal to 0 when 2x is equal to 3 and x is equal to 3 halves. And then 3x plus 2 is going to be equal to 0 when 3x is equal to negative 2, which makes x equal to negative 2/3. So we're going to list those values in order from smallest to largest. And then we're going to test our intervals. So if you want to do that graphically, that's fine. Again, this parabola opens up and it has 2x intercepts. So if it opens up and has 2x intercepts, that means that the vertex has to lie below the x-axis. So graphically, it's going to look like so, where this interval is positive, the middle interval is negative, and the last interval is positive. Okay, the other way for you to determine that is to numerically test. So if I pick a number smaller than negative 2/3, let's say I pick negative 1, when I plug negative 1 in the place of x, the first factor is negative, the second factor is negative, and a negative times a negative is positive. If I pick a numeric value on the middle interval, let's say I pick 0, the first factor is negative, the second factor is going to be positive, and a negative times a positive gives us a negative product. And if I pick a value bigger than 3 halves, let's say I pick 2, the first factor is going to be positive, the second factor is going to be positive. So that resulting product is positive. So we're again trying to find where this product is less than or equal to 0. So on what interval are we negative? It's on the closed interval from negative 2/3 to 3 halves. Okay, so for 3, I'm going to write the terms here in like standard form. So I want my highest degree term first. So that's going to be negative x squared. My next highest degree term next, which is plus 12x. And then my constant term last. Okay, so that's minus 36. Now again, I want my squared term to be positive for factoring purposes. Okay, so what I'm going to do is I'm going to multiply both sides of this equation by negative 1. So when I multiply the left-hand side by negative 1, we get x squared minus 12x plus 36. When I multiply the right-hand side by negative 1, we get 0. And if you multiply both sides of an inequality by a negative number, the inequality symbol reverses. Okay, so I want to see if this is factorable, which to determine that, I'm going to multiply the leading coefficient 1 times the constant 36. So that gives me 36. That goes on top. The coefficient of the middle term, negative 12, goes on bottom. So I'm looking for two numbers that multiply to give the top number and add to give the bottom number. And that is negative 6 and negative 6. Okay, which is going to make x squared minus 6x minus 6x plus 36. And then I'm going to factor by grouping. So I can factor an x out of the first two terms, which leaves me with x minus 6. And then I want to factor something out of the next two terms, which leaves the same quantity in the parentheses. So if I factor negative 6 out of the next two terms, that leaves me with x minus 6 as well. So x minus 6 is the common factor. When I factor that out, that leaves me with x minus 6. So this gives me x minus 6 quantity squared. So our only x-intercept here is at x is equal to 6. So if our quadratic function only has one x-intercept, that means that the vertex has to touch the x-axis at that x-intercept. Again, because x squared is positive, the graph is going to open up. So we are positive on both intervals here. So the intervals on which are positive is -infinity to 6, union 6 to infinity. And again, we're using parentheses here because our sign is greater than. Now, we can also numerically test the intervals. So if I pick a value smaller than 6, let's say I pick 0, -6 squared is going to be positive. So that first interval is going to be positive. If I pick a value bigger than 6, let's say I pick 7, 7 minus 6 is positive. When I square a positive number, that product is going to be positive as well. Okay, so that right there would be your solution in interval notation. So that graph is going to lie above the x-axis everywhere except at the vertex at x is equal to 6. Okay, let's take a look at number 4. So again, we have things set up the way that we want here. So we have x squared minus 2x minus 16. That's in standard form. It's greater than or equal to 0, so we're comparing that to the number 0. So, and the x squared term is positive, so we have everything like we want. We want to check and see if this is factorable. So I'm looking for two numbers that multiply to give the top number. So that's -16. And add to give the bottom number, which is -2. I don't know about you, but I can't think of two numbers for which that occurs, okay? Because there aren't like two integer or rational values for which that occurs. So factoring is not going to work for us here, which means we either need to use completing the square or the quadratic formula to test our intervals. So I'm going to use the quadratic formula. Okay, so again, we're going to get x is equal to -b. So -2 is going to be +2, plus or minus the square root of b squared. So -2 squared is 4, minus 4 times a, which is 1, times c, which is -16, all over 2 times a, which is 1. So we get x equal to 2 plus or minus the square root of 4. And then -4 times -16 makes +64, all over 2. So we get x here equal to 2 plus or minus rad 68 over 2. And then we can rewrite this here as x is equal to 2 plus or minus rad 68. I can break that up into rad 4, which is 2 times rad 17, all over 2. And then if I factor a 2 out of the numerator, we get 2 times the quantity 1 plus or minus rad 17 all over 2, and then we can cancel those factors, okay? So our zeros here are x is equal to 1 plus or minus rad 17, okay? So if we put that on a number line, our smaller value is 1 minus rad 17, and our bigger value is 1 plus rad 17. And then, again, because x squared is positive, the graph is going to open up, and if our graph has two x-intercepts, that means the vertex lies below the x-axis. So my intervals here will be positive, negative, and positive. If you want to pick numeric values to test, that's fine as well. Okay, and we're trying to determine on what interval are we greater than or equal to 0. So we are positive on the interval from negative infinity to 1 minus rad 17, union the interval from 1 plus rad 17 to infinity. Okay. See what you guys do with number 5. All right, so go ahead and pause the video, give this one a try, and then we'll talk about it together. Okay, so for this one here, I'm going to go ahead and distribute 2 on the left-hand side. So we get 4x squared minus 6x. And then I'm going to add 9 to both sides. And we want to find where that is greater than 0. Okay, so again, first thing we want to check, is this factorable? Okay, so the number that's going to go on top is 9 times 4, which is 36. The number that goes on bottom is negative 6. So I'm looking for 2 numbers that multiply to give 36 and add to give negative 6. And there are no 2 numbers for which that occurs. Okay, so factoring is out, which means we want to use the quadratic formula to find the zeros. Okay, so we're going to get x is equal to negative b, so negative 6 is going to be 6 plus or minus the square root of negative 6 squared, which is 36, minus 4 times a, which is 4, times c, which is 9, all over 2 times a, which is 4. And when we look at our discriminant here, that expression underneath the radical, the discriminant is negative, which means this has no real zeros. Okay, so if we think about this graphically, if that graph has no x-intercepts, and we know the graph opens up, okay, I know that graph has to open up because the x squared term is positive. The only way the graph opens up and has no x-intercepts is if the vertex lies above the x-axis. Okay, so graphically you're going to have something that looks like so. Well, when is that graph greater than 0? So if we're trying to find where that graph is greater than 0, we're looking for where that graph lies above the x-axis. And that graph always lies above the x-axis. So the interval for which this is a solution is going to be for all real numbers. Okay, so again, this should give us a pretty wide range of examples. We had to utilize the quadratic formula. For some, we did one where a vertex lies on the x-axis. We did one where a graph is going to have no x-intercept. So this should be a pretty good range of examples for you to know for your homework assignment and for future assessments that you're going to take as well. Okay, so that's it. That wraps up this lesson, guys. Hope you had a great weekend. We'll see you in class on Monday. Take care.